I'll set up my screen, okay? Okay. I'll go to the first screen. Okay, today's title, today's presentation, today's lecture is about feed of ocean plants and the procedures. So feed means front-end engineering design. So we'll learn about this. And we'll cover the first two topics in this part. The first one is design procedure of ocean plants and key project activities as some as case studies. And so this is slide that shows the meaning of feed. On the right, you can see a well-known EPC cycle, engineering, procurement, and construction. Mm, this is well-known. I think I've seen this before. And the players in this part are the owner or client. They're usually for our case oil major, and there is a EPC contractor. That's usually shipbuilding companies like Hyundai and Samsung. And so to the left, we can see a gray area that says feed, and that's designed before contract signing. So that means pre-contract design or base design. That's feed. That's usually done by client. They usually employ a separate company called engineering company to do feed. And after contract, as you can see on the right part, so the first part is feed done by the client. The second part is APC that's done by the contractor. And then there is, as you can see, there is turnover that is handing over the design to the owner or to the client. And then after so I after feed, there is at the two sides of this graph, there is con, contract contract. So after feed, there is contract between the contractor and the owner or the client. So after contract, big shipping companies make real APC cycle contraction, and there is handover back to the clients. For example, oil majors such as shale, and there is commissioning after handing over. That commissioning means the clients check if the, 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 the thing works or not. So as we have seen before, using analogy of home building, uh, first there is for the feed part. The analogy is the client or the owner of the house presents what he wants and also does some kind of cost estimation, and then there is contract between a home builder and the homeowner, and the home builder builds the house and that does everything, and then hands the home back to the owner. And after getting the fully finished home, the owner does commissioning. That means like checks if everything works, and that's what it looks like. So the horizontal axis on this graph shows flow of time, and the vertical axis shows amount of work done. So this is, yeah, this is each's FPSO project. An example, I think this is the northern part of Australia, and the contractor is Samsung for this project. Uh, this is a project organization chart, and Impex is an owner or client. oil major from Japan, and as you can see, circled by red, CPF and FPSO. That's one part of the big organization. And this is the chart of the overall flow. And this one is FIATEC, organization name, which specializes in BIM. As you can see at the bottom, there is something says building beyond BIM. BIM is building information management. In the middle, as you can see, there are phases. There are five phases: planning, design, integrated automated procurement, mm, construction, and operation. I think procurement maybe a new term, so I'll check for its definition. Mm, procurement, yeah. Can you see the screen? Eh, Can you see the screen? Oh, okay.
Yes.
So it's the act of procuring. So what's procuring? It's to get possession of, obtain something by, yeah. That means like handling. I think it means handling the parts. And so you can see the first step is planning, and it's planning similar to feed, and it's feed is a design for contract preparation. So this shows the players in this whole process. So as you can see, there is the company, that's client company. Usually they are oil majors like ExxonMobil, Shell, Total, and there is APC, the APC contractor. I'm not sure about these companies what they are. So, but they are generally the ones that do the that take over the process after contract with the oil company, with the client, or in our case oil majors. And there are other two companies that work with the contractor, that are suppliers, that usually I think procurement that's what happens from them. And there are subcontractors. The EPC contractors might hire subcontractors to do some tasks. As you can see Samsung Heavy Industries is in this section. I think Samsung Heavy Industries is now in the EPC contractor section. They used to be subcontractors before 10 or 20 years ago, but now they managed to also take projects as main contractors. So these are the main actors in this whole process. So this is the procedure life cycle in the subsea system, but can be applied to ocean plant. So there is concept screening at the first part. This is early stage of planning, and then there is a feed. And as you can see, if you can see, there is a blue, something written by blue. It's added, I think, after this slide is made. So after feed, there is contract signing between the client and contractor. Then you can see detailed design, procurement, project management. So the detailed design is done by the shipbuilding company, and it goes comes and there is construction and installation, and everything's done, and then there's handing over back to the owner, and then there is operation and integrity management by the owner, and then there is relifting and decommissioning. This is usually like maintenance or repair, or even may include abandonment if it's like required. But this is done according to the interest of the client. So as you can see, there are 2 points: contract signing and handover. Everything in between this is done by the client. So another similar procedure, but this is in the viewpoint of equipment supply. Equipment procured by equipment suppliers, like by companies like Mitsubishi and General Electric. So as you can see, there is design. This is the beginning phase is design, and then there is procurement, then there is manufacturing. So those things also need to be manufactured, and then there are the They are then shipped, a shipping process, and there is installation done by the equipment suppliers. Mm, and then there is construction and erection. Usually this is done by when both the equipment suppliers and the contractors are present, engineers from both companies are present, and then there is inspection and testing, and then there is handing over to the main contractor. So we can take, for example, boiler as an example. So they first design and then they do the procurement and manufacturing and ship it to the shipbuilding, in the how can you call it, the main contractor, and then they install it and then hand over to the main contractor. So this is cycle in terms of stage. Mm, so there's as you can see, the third to the right part there is feed. That's what we're looking at now. But before feed there is something called pre-feed 2, basic engineering and conceptual cycle. Then before even that there is business planning phase. This is just very beginning, so there is no engineering work done here. There is no drawing and stuff, but it's just basically from business point of view. They define opportunity, and they do technical assessment and milestone schedule, estimate the cost, and basically what they come up with is a requirement and economic evaluation. That's done by the client or by the company. And then there's pre-feed. That's basic engineering and conceptual part. So they also evaluate alternatives, confirm feasibility, and develop process design. And also they make some rough estimate of the cost. And then layout, and this is done by the contractor, and also the feed is done by the no, yeah, by the contractor. Yeah. So they refine the cost estimate from the previous stage, and they also do some kind of estimate of the cost. So error rate is really a big part of project, because basically this project is in terms of billion of dollars. So 20 or 30% cost is, that's a lot. It's not a small amount of money. So it's really a big factor here. So this is the what the project development phase looks like, and then the feed and pre-feed part. So this is ship design spiral. This is done, I think, from viewpoint of naval architecture, from naval architecture side, but similar procedure for for other complex systems also works. So as we can see, there is naval architecture, structure, propulsion and machinery, auxiliary systems, electrical systems, outfitting. Mm. Then there is concept design, functional design, and detailed design. So this comes, and at the end, at the center of the circle or the spiral, we finally finish up the design. This is where it ends. So this is the Ford Mustang model. So it's labeled as ugly car. I'm not sure, but I think this is because of the hood shape. So mm, this is to show the importance of collaboration between teams while designing a system. So for this car, there is outer skin designer, and then there is engine designer. After the outer skin designer is After the outer skin design has been developed, it's found out that the engine is so big and it cannot fit into the hood. So then the hood was expanded and it became so big. So then that made its appearance to be ugly. So this problem happened because there was no mm, collaboration between different domain experts. So these things may happen if there is no collaboration, and strong collaboration between teams is required. So as you can see, the hood of the car is so big, and yeah, it may have influence, because sometimes some products like car their appearance might be important for customers. So this is another spiral, but similar with a bit detailed explanation and more stage. Four stages. There are four stages as you can see at the bottom, marked with rectangle and circle. There is concept design phase, mm, and preliminary design phase, and there is contract design phase, and at the end there is detailed design phase. Mm, Usually, sorry. So you can see now it's to like counterclockwise, using requirements, proportions, and preliminary drawing, then hull form design, floodable buildings, and freeboard structure, powering, and comes to cost estimates. Yeah, and okay, this is the bit detailed, but yeah, similar spiral. So this is now it's like the previous one is circular, but now this is like this is more linear in one way. As you can see, mm, there are two graphs: graph of influence and then project cost. So influence, it's kind of chance of modifying the design at the beginning. Like as you can see, there is a main milestone as this line, a kind of bold reddish or purple line. That's the contract phase. So before that, there is feed and pre-feed. And influence. So this part before this bold line, it's mainly by the client or by the owner. So the influence is here is very big, and shows that the early design stage is very important for plant and for plant and engineering. So as you can see, it's like the influence gets really low after the contract. So that means it becomes really like nearly impossible to modify the design. So the, the feed and free feed part are really important stage. And for the project cost goes up after the contract, because this is where the real engineering starts to occur. So this is what it looks like in a linear fashion. There are detailed design, construction, commissioning, initial operation, and then there is steady state operation. Okay, this is what it looks like in a linear way. Mm, so as you can see here, these are the key project activities: front-end loading, project execution planning, risk and opportunity management, operation readiness and assurance, and management of change. As you can see here, this is once again a similar process as we have seen before. There are 5 phases. The first one is identification, second one selection in yellow, and defining and execution and operation. As you can see, there are like at the right end, there are something like A, B, C, D circles. So um, it's labeled as good project execution and poor project execution, like A and B respectively. So and C and D are also like very poor project definition. So this shows like at the early phase, the selection and the identification phase, this is really influential phase. It makes or breaks the project. So as you can see, good project definition, that means the good project definition like affects how much successful the project can be. So if the definition of the project is really poor, it's going to end up in really bad state, as you can see C and D. So as you can see on the left end of this graph, it shows the value, the y-axis. So this means C and D have really low values because it was screwed at the beginning and in the project definition part. So it has a really big effect. And at nearly the end, there is project execution. It may also be good or bad, but there is small influence. It's not much. It's not as much as the influence of project definition is. So as we can see here, A and B are in good state, but still A is better. And then C are D are really in a bad state, bad value. This is the same graph as we said before, just it's enlarged, magnified. And this is concept engineering. This is pre-DG3. DG means decision gate. Pre-DG3 engineering activity in support of project development and is closely integrated with subsurface field development planning for oil and gas developers. So as you can see, identification, there is identification phase, and there is assessment, and then selection goes on. So these are the main deliverables. As you can see, the identification, there is project initiation node, the assessment, maybe feasibility study report, and the final selection part, there is field development plan. Mm, this is basis for design, BFD, as we call it. Here, this part output is collection of requirements. So all projects shall have BFD. So this is where the requirements come from. For all projects requiring engineering definition, this basis for design shall be completed prior to design gets ready. As you can see, there is before design gets ready means mm, after identification, assessment, and selection, all project requirements should be defined at this point. And then after definition, there should be some contract contract signature between the contractor and the owner. Mm, so there is some video we can see. Can you listen to the voice? Is the voice like? Can you hear the voice of the video? Okay. Start. So at the beginning, the color is gray tone. This is because of so I think it's around here. Yeah, here it's gray tone because it's laser scanning point cloud of the constructor plant system. As you can see, this equipment here, like, sorry, yeah, this one is, yeah, lidar maybe. The color is gray tone because it's laser scan point cloud information of the constructor plant 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 system. The later stage, based on this point cloud, a color card model is built. I think it's for the color base. Yeah, this one. Color card model is built and fully built card model is shown then. This is accurate 3D card modeling and production of 2D planes. And then there is, if this is fully built card model. Yeah, should go back. So this is the stage 3 of feed system. So after feed, there must be contract signing stage. Uh, the front end engineering design, that's feed, develops the requirements of BFD into design. So in the previous stage, BFD stage, we developed requirements, and now we're developing those requirements into design deliverables, leading to the project specification. And then there should be, after that, this point, there is contract signature signing between the players, which are the owner, that's that's the client, and then there's contractor like Samsung and Hyundai, and that's what happens. Yeah, and that's it for today. Yeah, if you have any question, yeah, feel free to ask. Yeah, I'll try to answer them. Thank you.
All right. Question. It is a rather complicated lecture inside content, so you may have many questions, I guess.
Yeah, I'll try to answer to my abilities if there is.
Then you can raise a question. Bracket yourself.
Me?
Yeah, why not? Because it looks like that the student does not understand. Less understand than you yourself, right? Anyway, there should be many questions. All right, so we don't have questions, then we can have a 5-minute break and then return back to my lecture, second part, because there is no discussion session today. All right, so we see 36, 136. Can we start the lecture? Do you have any question? No, and I can continue my lecture. So here is the lecture note. Second part. Procedure feed. It is a front-end engineering design. As Burke says, it is a pre-contract design. So contract is very important because you should have a legal assignment about the performance and also the price and also time, delivery time. So something is wrong with this contract, then there can be a lawsuit. So that create complication. So before contract, you should have enough knowledge to make a firm decision on contract because it's a legal binding. That's why the feed is important. All right, second part is about concurrent engineering and design change management. Okay. And so SCM is supply chain management. So this plant engineering, the feed, because the plant is ocean plant is complex, and there are many parts, probably millions of parts, and there is a dependence between parts. So you could say interdependent among parts or equipment. And also the system itself, the plant itself should be independent from others because it is floating far away from the land. So there is no cable, no street, no way, no communication sometimes, no energy delivery through the electrical cable. So it should be independent operation. And then the security, because there are many cases of fire and explosion, because it handling mainly the gas and oils. So that good management is important. There is an oil leak explosion in more than 20 years in North Sea or Europe. So let's see the video of this disaster.
이 조절식 안경은 세계를 휩쓸고 있습니다. 이 제품은 언제 어디서나 완벽한 시력.
A spark of Scotland. The Piper 1988. 120 miles northeast of Scotland. The Piper Alpha oil rig. At 14,000 tons and 2.5 times the height of the Statue of Liberty, it is one of the largest rigs in the world.
Piper Alpha was the world's most successful oil rig. What that means was that in a single day, Piper Alpha produced more barrels of oil than any other oil rig or oil platform in the world.
A crew of 226 rotate shifts to keep the oil and gas flowing. Jeff Bollins is the chief control room operator that evening. At 9:45 p.m., Jeff suddenly hears an alarm, indicating a problem with one of the rig's condensate pumps.
Them condensate injection pumps tripped more than any other equipment we had. No panic, we knew we needed to get it back on because it was going to start affecting production.
That evening, Pump A is offline for maintenance, leaving just Pump B working. The same pump that's now been shut down by the alarm's trip system.
The condensate pumps were an integral part of the production facility. You couldn't have them both offline for any great length of time without shutting down everything.
To avoid a full shutdown, a decision is made to halt maintenance on Pump A and bring it back online. But what nobody knows is that Pump A has a fatal flaw. During maintenance, its safety valve has been removed, meaning that there is nothing to stop thousands of cubic feet of gas escaping into the atmosphere. The faulty pump is switched back on. Then, at 9:55 p.m., disaster. A spark suddenly ignites the escaping gas, and an explosion rips through the rig. Confronted by 700-degree flames, most of the 226-strong crew are now either dead or severely injured.
The nearest analogy is that it was a cross between Titanic and the Towering Inferno.
All hell was breaking loose on that rig. It was just a scene for hell. It's the only way you could describe it, a scene of absolute carnage and hell. Flames, explosions, debris. Things were escalating so fast at that point that it was almost impossible to take things in.
By 10 to midnight, less than 2 hours after the initial blast, the Piper Alpha is on the verge of collapse. Finally, the rig's legs start to give way, and the Piper Alpha starts to slide into the sea.
Where A module was and the rest of the platform just started drifting apart. And the other 3/4 of the platform just very slowly fell into the North Sea. That's my worst memory of the night, because I know for people who were still on it, it would have gone to the bottom of the sea.
A total of 167 men lost their lives that night. Just 61 survived.
Okay. So that's the story behind the big disaster in North Sea of Europe in 32 years, 33 years ago. Oh, long time ago. Right, here is a design process again in different format. Here the center is locating the engineering. So this is to see the design as the centerpiece of the whole process, because design is the main part of the engineering. Now, the client should be owner of the plant, mainly the oil major companies such as ExxonMobil or other Total, Amco, and then the client gives you to the engineering the comments and approval. And the left-hand side, the client gives you mainly the design basis. So this can be the requirements, design requirement, same as design requirement. So functional requirements, and then also client specification means sometimes client fix their equipment very technically. Say something like when I buy my car, I may require the car maker of say audio system, and also sunroof, and sometimes tire. Maybe I like a tire coming from say France, so special tire can be attached. When I build my home, I may choose my own chandelier or kitchen facility, or sometimes toilet, bath. So that kind of thing is fixed by client. So in shipbuilding or ocean plant, client usually fix important major facilities, some of important major facilities, including many times the engine, main engine. And design code is regulation, standard. So that is altogether can be design basis. So engineering or design team start from design basis and produce document. So document is something like a drawing or CAD model submitted to the client, so that client is comparing the design basis and requirement, and then document prepared by engineering, and then they can approve to go ahead, or they may comment to modify, improve some of the document. And the engineering department start buying procurement of equipment. So that equipment suppliers, they call it as a vendor. So the vendor start to design their own system, something like an engine, propeller, or other items, cranes, or special facilities, pump and other boiler. So that they also produce their design drawings or CAD models to the engineering company. of each equipment, because there are so many equipment, including several thousand of them, they should purchase. Then after many cycles of design changes and improvement, based on comment, the document for construction is delivered to the construction department. There is a construction drawings and right-hand side in red color and specification. And also document for purchase goes to the suppliers after fixing which one to buy and which how many and what level of quality. So it is a bill of quantity and specification is given to the purchase department and also to the vendors. There is a process. Again, this drawing is same, but the right-hand side is more elaborated, including cost estimation department and inquiry and pink color. So vendor is upward now here, and vendor and also subcontractors. So they inquire and quotation. It goes many times, iteration, and there is a negotiation between purchase department and also vendors. And also client in the bottom of right-hand side, the engineering basis for EPC call for tender, material requisition for contract, and then there is also engineering. So deliverables is DLV. So that the EPC company, something like such as Samsung Heavy or Daewoo Hyundai, they also have a big contract with the client, because engineering is for only design, say something like a feed. After design is mature enough, then the client should have a contract with the EPC construction. Now, what is concurrent engineering? It is moving from sequential to concurrent execution of engineering activities. So in top lines, there is a sequential activity of engineering, procurement, and construction. Right? EPC, E and P and C goes one by one. So it is the old way of working. So design is finished, then we start procurement, and then we construct ship or plant or home. Right? That is very natural way. But in concurrent engineering, there is some overlapping activity between 3 EPC cycles. Why? They want to reduce time to market. So whole time to delivery is reduced by something like 10% in this figure. That is a big advantage to involve the people, including client and engineering and also EPC. In terms of cost, can be lowered down, and also delivery helps to the system can be used as an operation to produce oil and gas. So it also helps to clients. That's why they want to reduce the time to delivery as much as possible. The problem is the quality of the system can be lowered down because of this complicated activities and process. So nowadays we can try to do these ways. So in old days, the sequential execution, the engineering, the design, they produce drawings and bill of materials for the purchase. And then procurement department start procurement, working with vendors or suppliers. And after procurement, we can start construction, the real manufacturing. Right? That is the sequential way of doing in old days. Now it goes in this way. The engineering cycle and procurement cycle and construction cycle is overlapping, right? In terms of timeline. Not after the previous one is finished. The later stages start earlier than before. Right? So bill of material should be coming multiple times because design is going on and procurement is already started. So bill of material coming in series of set of purchase. And also in construction, the drawing is coming in terms of multiple versions of drawings because the design changes after procurement started, also construction started. So that there are small changes after construction started. So new updated version of drawing is coming late. So that the challenge, the complication or difficulties can be design input should be coming earlier as possible. And then there can be many changes during procurement and during construction. So how can we reduce number of changes? And also because of the change, there can be a rework of procurement or rework of construction. And then integration among EPCs work process. In old days, sequential activity, there is less need for integration. But now, because it is going parallel, concurrent, they should communicate more tightly because there are changes which is affecting the other part of EPC. So at the bottom, they are saying data consistency, configuration management, engineering change management should be done, necessary for the concurrent engineering. Right? So this one looks like equipment purchase and delivery and installation cycle. And at the starting point, the process simulation, they decide equipment, which equipment and also what size and how many is fixed. So it is coming from design. So chemical process simulation output can be the equipment specification. And then the purchase department start a procurement, so inquiry and selection from the vendors or suppliers. And then the vendor start their engineering. Engineering means design and manufacturing. And then they produce their own design and drawings, and also including foundation drawings. Foundation drawing means if it is installed to a ship or plant, they need some kind of foundation, which is attaching this equipment to the ship or plant. Say you can expect installing air conditioner to your car or your home. You need to ask engineers to install the system. For installing an air conditioning system, you need to have a hole through the wall or window of your home, because there are two parts of air conditioner. One is inside indoor unit, and also there is another unit for outdoor, right? And they should be connected to each other by a pipeline. So installation requires some activity, including and foundation and other things, cabling and piping. So at the left-hand side, they are saying engineering is the integrator of the plant equipment and is highly dependent on vendor data. Vendor is a equipment supplier. Right? Questions? Otherwise, so, but for the concurrent system, you need to have a well advanced calculation and simulation or check. So engineering must be right at first time, which requires experience and coordination between different disciplines and anticipations. Say here, example is a safety valve, inquiry and purchase, size and drawing, and location and piping routing, and piping calculation and support, steel structure design and drawing. And then you need to have a purchase steel, fabrication, shipping, and structure at site. Then you can go do installation. Okay. But if there are some problems, say number of valves or size of the valve is changing because of, say, process simulation or because of the installation foundation, there are many cases of different changes. Anyway, then you need to do same thing again with different changes. So it can take another cycle of work. And another problem is you need to purchase a little bit different pieces of steel and pieces of valves. So that creates a time delay and money spent, cost high. So how can we avoid or reduce number of changes, design changes? We call this is change management. So there are so many sources of changes, including technical issues. Technically, there are problems. That is very fundamental issues. And also there is a design development and reviews. There is a comment coming from client, comment coming from designers, comment coming from vendors, or can request small changes. Right? And also client has, they change their mind so that they have a new requirement. Say something like, I want to put my different audio system to my car, or I might change my color of car. So painting should be done differently. Or may I change my mind to do the interior of my home to install a more big TV set with a surrounding audio system. That kind of thing can happen during the construction of ship or construction of home. And third party at interface. Third party can be the supplier mainly. And supplier also have their own supplier too. So there is a layer of supply chain. We call this supply chain management. So there are interface between suppliers layers. There are delays, there can be changes, there can be materials different. Or sometimes if we outsourcing equipment from international country, not domestic, there can be a problem coming from different countries, language problem, metric problem, other things. So we want to reduce design changes. How can we do that? So avoidable changes we try to avoid, right? And contract should be well managed, and any change gives you an impact. And if change is coming late, then it can be exponential with time. So the change can be done in early stage of the design. That's much better, rather than if the change is coming in late stage of the construction, it can give you a very big problem. So interface management, interface between divisions, department, design and construction and procurement. There's a major three department. The communication interface between here is important. Also, the client communication with the suppliers also, right? So how can you identify an impact and change implementation should be well managed through the design change management system. So supplier and subcontractor, how can you control them? You get what you inspect, not what you expect. Right? So inspection of contracted equipment should be important. And also how they work, the supplier work process and steps, so that you can expect the delivery time and also level of quality. Right? And then tight follow-up and expediting should be required, and also the success suppliers software system or information system is also helps, but there should be a limited access naturally, so that quality and delivery of suppliers is important to whole process of engineering of construction. Say, imagine that the main engine of a ship delivers, say, 1 month later than scheduled. Then what happened? You need to wait until main engine is coming, because main engine is located in aftermost part and also the lower place of the ship. So if you don't have a main engine, then you cannot connect them to the propeller, you cannot connect it to the, and also you cannot closing out the engine room space, so that above structure cannot be constructed if there is no engine is coming. So scheduling is important. Now, the project organization, this is not whole energy company. It is only for EPC company. So project manager has engineering manager, procurement manager, site manager, and project control manager. And under them, there is a project engineers, discipline engineers, purchaser, expenditure and inspection, construction manager and contract manager, scheduling manager, and cost control. So there are many people are involved. And process of design, the chemical process design, because it is ocean plant is going on with oil and gas. So chemical process design is in early stage, or feed design is early stage design. Among them, the process design is earlier, right? So process flow diagram is the starting point, probably for the chemical engineers, they know as well about this one. And material balance for chemical reactions and energy balance. And then finally they get the equipment data sheet. How many pumps, how many valves, and also heating coils and other things. It design determined based on flow diagram, process flow diagram. And then they can start to draw a drawing called PNID. And then also in right-hand side, there's a utility flow diagram. It is similar to the process flow diagram, can be the main line, main flow line, but utility also has there's subsidiary flow diagrams. And then finally, based on PNID, there is an operation instruction and positive, something like suction head. Right, so process flow diagram or flow, the process engineering is a chemical process engineering. Our work involves most of the basic design of design basis is coming, basis of factory design, and design result directly affect the detailed design in later stage. So PFD, the process flow diagram, PNID, pipeline instrumentation diagram, and utility flow diagram, important and baseline for further activity. Now, it is an example of PNID drawing. So you see that there is a NH4SO sulfide and nitrogen solution and wash buffer and the dissolution buffer. There is a external pump and there is a stirred reservoir, and then black pressure valve, and then membrane module, feed pump, and fraction collector. What is this? Column and valve again. So that kind of thing, we call this is a PNID. So that symbols are used, and then lines are pointing the pipelines, and also dotted line can be the cables, electrical cables for the control and sensing. So output can be equipment data sheet. That is selection of equipment, how many, which kind of equipment. And then also we need to have a safety and also pipe process data. Piping is most important portion of the construction because there are many pipings between equipment. Instrument usually comes with electrical control and safety and some sensors, data collection. So it is electrical process data, and line scheduling is also important. So it comes with the equipment list, operational manual, and interlock scheme. So let's see what is how can we read the PNID? Okay. So it's some example.
In many of our RealPARS videos, we discuss control system and instrumentation devices in great detail, so you can understand exactly how they work. In this video, we will learn how to read a P and ID, which is something that engineers encounter on a daily basis. At RealPARS, we love helping you learn. So if you enjoyed this video as much as we enjoyed making it, click the like button. Subscribe and click the bell, and you'll receive notifications of new RealPARS videos, so you'll never miss another one. PNIDs, or piping and instrumentation diagrams to give them their full name, are schematic representations of pipelines, equipment, instrumentation, and control systems found in process environments such as oil refineries, chemical plants, paper mills, and cement plants, etc. The symbols contained in PNIDs represent the equipment in the process, such as actuators, sensors, and controllers. Process equipment such as valves, instruments, and pipelines are identified by codes and symbols. As well as devices and pipelines a PNID will commonly contain, information on vents, drains, and sampling lines, as well as flow directions, control I/O, and interconnection references. The instrumentation codes listed in PNIDs follow a standard format. After some practice in reading PNIDs, you'll know these codes by heart. But in the meantime, there are many resources on the web where you can download these tables for reference. The first letter of the code identifies the parameters that are being controlled or monitored. For example, flow, temperature, level, or pressure. The next letter is used to define the type of control device being used. For example, transmitter, valve, or controller. The number refers to the logical numerator. For example, we may have a system with 4 temperature transmitters. It makes sense to identify these as TTO1, TTO2, TTO3, and TTO4. Let's consider for a moment an instrument on a PNID named FV01. Looking up the code for this, we could tell this is a flow valve numbered 01. Symbols, circles, and lines are used to represent instruments and to show how they are connected to the rest of the system. Now that we know our device, FV01, is represented by a circle, we can also tell from the PNID where the instrument or device is located. The presence or absence of a line in the circle determines the location of the physical device. Let's take a look at how these are commonly represented. No line. The instrument is located in the field near the process and operator. Dotted line. The instrument is located in a control room, accessible to the operator. Solid line. The instrument is not directly accessible. The piping or connection lines on the PNID also tell us about the instrument. For example, a solid line would indicate the interconnection is via pipework, whereas a dotted line would indicate an electrical connection. It is worth...
Let's stop here. Questions? Otherwise, we can continue and finish our lecture today. So, the process design is for, you can say, chemical process design. It comes with a PFD and PNID and piping instrumentation, so that they need to have a purchase equipment specification or equipment data sheet. Then they can purchase and lay out construction. So there's a topside engineering. Topside is something like in ocean plant engineering, they said hull, because the ship, it looks like a ship. Which one is supporting the chemical plant itself, which one is usually located in land side. Now the land side, the chemical plant is coming toward the ship offshore in ocean. So that the original chemical plant, we call this is top side. And the bottom side is, we call as hull of the ocean plant, which is providing buoyancy and motion because it is floating. So the topside engineering is very similar to the engineering for chemical plant in land side, but there is small difference because of the interaction with the hull, because it is floating. Okay, that's it. So time is up almost on. So if you have any question, no questions. Then let me see the schedule again. Oh, next Tuesday we will have a project midterm presentation. No class, all right? No lecture. There is a class, but no lecture. All right, see you on Tuesday. Bye now.
Thank you, Professor.